All right, batch normalization and regularization. So batch norm. The idea behind batch norm is it has been known for a very long time that normalizing your inputs helps. And we'll talk a little bit in a minute about what I mean by normalizing. What if we could normalize the activation of every layer, right? So if we had a network like this, right? And I'm going to call sort of, here is our inputs, right? And then this, our first weight layer and first activation, right? So our first weight layer and activation is layer 1. And then our second weight layer and activation is layer 2, okay? So if we think about it like this, we've known for a long time that normalizing our inputs, right, as they go into the network, improves training. Could we normalize the output of layer 1 as it goes into layer 2, and would that speed up training? The answer turns out to be yes. Okay? What do I mean by normalize our inputs? I mean transform them so that their mean or average is 0, right? So if we have an input x, we transform every x in it so that the average across x is 0. And then we transform them so that their variance is 1, which we'll talk about in a minute. Why do we do that? So that we stay in the useful region of the nonlinearity, and so that one input doesn't dominate training. Okay? We can skip that for the moment. So, a mean of 0, right? Why does that help? What do I mean by stay in the useful region of the nonlinearity, right? I mean, being more likely to stay in here, right? So this is tan h of y, and this is tan h prime of y. And we saw these last week, right? And we kind of have a useful region, if you look at it, which I've sort of loosely blocked out here, where the gradient is large enough that we can have error backflow, right? This is the vanishing gradient problem again. And if we get out of the useful region, if we land up here in the saturated region, then our gradient is tiny and our error signal goes away, right? So what does that have to do with the average value of x? Well, if the average of x is large, right, then that means we are more likely to see a large y. So if the average of x, so let's kind of think about this graphically for a minute, right? If the average of x is displaced away from 0, right, that means that the data set x, right, probably looks something like this. Which means that the result of translating it with wx plus b to produce our y, we are more likely to see a large y, right? So if the average of x is displaced away from 0 by some large amount, then our y is more likely to be large, right? If our y is large, then we are likely to have a lot of our sort of, right, little y in y, our individual activations, land in the saturated region of tan h. And if they do that, we're going to get, right, no gradient. And if we do that, we're going to see slow or no training because of the vanishing gradient problem, right? So moving x, offsetting x, right, so that the average becomes 0, makes us more likely to have smaller y, more likely to land in the good region, more likely to get a usable gradient. Variance of 1, right? So we want a variance of 1 so that one input doesn't dominate training. What does variance mean? Variance measures how far a variable spreads out from its average value, right? So if we have two random variables, right, that we're looking at possibly as input, they might both, right, they might both have an average of 0. And here I'm using double bar to denote average, right? But one of them might have very extreme values, right? R1 might run from -100 to 100, while R2 only runs from -1 to 1. Well, again, think about transforming this with something like a forward pass, right? The weight layer of a forward pass. If for like an x that is sampled from -100 to 100, you are more likely to see a large value come out of this than an x sampled from -1 to 1, even though they have the same average, right? So again, you potentially run into the vanishing gradient problem, but you also run into the problem that our update multiplies by x, if you recall, right? So you might start to see this very high variance variable start to dominate the updates, right? And that could be a problem because the high variance, right, the extreme values, don't necessarily mean that this is a useful variable, right? This variable might add very little information that we care about, and so we would hope that it would actually sort of play a very low role in training, but just because, its values are so extreme, it might dominate training and weight updates anyway, right? So that's why we transform the variables, or the input, so that their variance is 1, right? Variance is standard deviation squared. We want the variance to be 1. And I'm not going to talk about the math that you actually have to do this, even though it is not incredibly hard, because we're going to find out there's an automatic tool that will just do it for us. All right. So if we're talking about an internal layer, there is a third problem, right? And that's a thing called covariate shift. So as the network trains, the mean and variance of a layer's output will move around, right? That is called covariate shift. The problem is the following layer has to keep up with that change, right? The following layer has to keep up with not only changes in the sort of average behavior of the previous layer, behavior in terms of sort of how it responds to its input, but just the mean and the variance of its outputs, right? As the network trains, right, if some output unit on some hidden layer starts to output extremely large values, right, then the fact that its variance is increasing might cause it to dominate training, and following layers might have to learn to shrink those weights. If this thing starts to output the same kind of values, right, but restricted to a lower range, then the following layer will have to adjust its weights to keep up with that change, even though the actual sort of dynamics, right, aren't changing from this thing. It's representing the same rule, it's just scaled the output of that rule to a smaller area, right? So basically, besides all of the normal reasons that you'd want to normalize your activation, we also have this covariate shift thing that makes like moving mean and variance even worse in the interior of the network, right? So if we would like to normalize, and the question is normalize over what, right? So if we are normalizing over our input, we can do that once. Basically, you loop over sort of, all x in x. You compute some statistics, you apply a transform, and then you're done. On the interior of the network, right, again, their behavior is going to be moving as their weight layer changes. So you have to continuously collect those statistics and adjust the output. And you potentially have to do it over an entire epoch, right? I guess if you wanted to do it most mathematically correct, or possibly most naively, you would do the forward pass of one layer for the entire epoch, and then normalize, and you'd do that every epoch, and then you'd repeat, right? Layer 1 for an entire epoch, normalize, layer 2 for an entire epoch, normalize, layer 3, so on. And only when you finally got into the end could you do the back pass for one epoch. That is obviously insanely expensive and inefficient. Well, the solution is we normalize over, a mini batch. So a mini-batch is similar to SGD, stochastic gradient descent, the thing that we've been doing, right? Stochastic gradient descent, you pick one sample at random, compute the forward pass, then compute the back pass, then apply the update. SGD, you pick k samples at random, where k is significantly smaller than the entire size of x, right? Maybe, I don't know, 50, 20. It's somewhat arbitrary, right? Then you compute the forward activation for each of the samples in k. Then you compute the backward pass only for the samples in k. Then you average those updates and apply them once, right? This offers a kind of useful compromise between stochastic gradient descent and full batch learning, right? We get quicker updates, we get a lot of the benefits of SGD, but it's more stable, right? This is a slightly more stable method than SGD is. The only real downsides of it are that it is slightly more complex to implement, not hugely, and you have to pick an intelligent mini-batch size, right? The size of that mini-batch, the size of k here, becomes another parameter that you have to have some intelligent selection for, and changes in which can have potentially surprising effects on the training dynamics of your network, right? So mini-batch learning is not specific to batch norm at all. It's just a general thing, but batch norm does require it, right? Batch norm requires it because we have to average over that mini-batch, right? That's kind of how it's defined, right? We are going to normalize over the output of our mini-batch. So I'm not really going to talk about how we do that. One is that it is not hugely complicated. The other is, again, TensorFlow just does it. It ends up being very easy to just turn batch norm on. So pros of batch norm from the paper that's linked before: it speeds up training potentially dramatically. It allows us to use a saturating nonlinearity like tanh even for a very deep network, in theory. Again, where sort of deep can have differing values, right? So what we mean by deep can change from slide to slide, right? But for some meaningful definitions of deep, we can get away with using tanh even for a deep network if we batch norm. And it also, in theory, allows us to use much larger learning rates because it will help the network to be stable. So large does not mean like near or over 1, right? We're still talking about learning rates like 0.1 or 0.2, but our network, will be stable potentially even with these as opposed to a learning rate of 0.01, say. The bad, what's the downside? Extra computation, right? You still have, and memory. You still have to record the activation of every sample in the mini batch, and then, you still have to record the sample, you have to record the activation, words are hard, of every sample in the mini batch. You have to iterate over it once to get your statistics, then you have to iterate over it again to normalize, right? It is not incredibly computationally expensive to do this, right? It doesn't swamp all of the benefits of batch norm, so people still do it, but it is expensive enough that I have seen people sort of talk excitedly in papers about ways to get the benefits of batch norm without having to do this, right? It's expensive enough that people have been motivated to try to find a way around it, right? And I know that is not an incredibly scientific way to talk about the cost here. I apologize. But yeah, how expensive? Not enough to stop people from using batch norm, but enough that they care about finding a way to get around it. So batch norm in TensorFlow is incredibly easy. It's just a layer, right? You just insert the batch normalization layer, and that's it. You will have to do this at every layer whose activation you want to apply batch norm to, right? So this is going to apply batch normalization to the output of the logical layer defined by this weight matrix and this activation, right? And if we had more layers down here, we'd have to keep doing keras.layers.batch-normalization. But that's it, right? We just put a batch norm layer in, and it will, it will normalize it will normalize the activity of the layer. And that should, if you do it at every layer, dramatically speed up training. This is also why, even though normalization has been known to help for a long time, I haven't mentioned it before, because we can normalize our inputs for free just by putting batch norm right after the input, right? If we do batch norm first thing after the input, it will basically normalize our inputs for us without us having to do anything. So, the batch norm paper is one of many papers that includes the perhaps overused phrase, acts as a regularizer. So, batch norm is claimed to act as a regularizer. Well, what is a regularizer? What does that mean? A regularizer is something that prevents overfitting. So what they're saying is, networks that use batch norm overfit less. We are now about to talk a little bit about regularizing and overfitting.